Hello, so what we're going to do is take a look at how we can use a fundamental theorem of calculus where we input our upper and lower limits to actually solve real-world problems. So what we're going to do is take a look at this problem right here. And what we're actually going to see is what it means when we are solving for this. So what happens is when I'm given a graph, right? If I were to give you, this is my lower limit A, and this is a lower limit B, we've been calculating this area underneath the curve. Well, what's actually happening is this is showing us our change in the function f of x between a comma b. So if we know how much something is changing and we are given an initial condition, we can actually find out an n value for this, and that's what we're going to use this theorem for. So if I wanted to do some algebra, I would be allowed to add in an f of a on this side and an f of a on this side, right? By algebra, aren't I allowed to add in an f of a here and an f of a on that side? Well, if I wanted to rewrite this, I notice these f of a's cancel, and what I'm going to do is flip everything around, and this is going to give me f of b is equal to f of a plus the integral a to b f prime of x dx. And so what we see is we can find an n value, because that's our upper limit, right? If we are given an initial value and if we are also given this change in f of x between a certain point a comma b. So what we're really doing is we're still going to calculate the fundamental theorem of calculus, but we're going to be able to use it by adding a little more of algebra to solve some of these problems. So our problem right here says if f prime of x is equal to 4x cubed minus 3 and f of 2 equals 7, then f of 5 is equal to question mark. So what we see is we have a change in f prime, or I'm sorry, in f of x right here, right? Isn't that what a derivative is? We also have an initial condition that states that this has to be true. Condition. And we also have an end value. So what we're going to do is we are going to follow that exact equation, and I'm going to get f of 5, my end value, is equal to the initial value, f of 2, plus the integral of the initial value 2 to the end value of 5 times my f prime of x. So 4x cubed minus 3 minus 3 dx. So now I just do the algebra. I'm going to scroll down just a little bit. We know we are looking for f of 5, and it's going to equal f of 2, which is equal to 7, plus, and I'm going to take this integral, 4x cubed is the same as 4x to the 4th over 4, which gives us which gives us x to the fourth minus 3x. And what I need to do now is just plug in my upper limit of 5 and my lower limit of 2. And so we just continue the algebra and we get 7 plus the parentheses 5 to the fourth is equal to 600. Oh, well, let's just write it down. 5 to the fourth minus 3 times 5 minus parentheses 2 to the fourth minus 3 times 2, close parentheses, and we get 7 plus, this is equal to 625 minus 15 minus 16 plus 6, which gives us 7 plus, and I'm going to add this and this to give us 631, and I get negative 15, negative 16 is negative 31, times a positive is negative 31, and we get 7 plus 600, which gives us a total of 607. So f of 5, given our initial condition and our change, has to equal 607. The good thing is we can also do this with our first graphical method using geometry by doing the same exact thing. So what we'll do is we'll set up our functions, and then we're going to take a look at what part of the graph is important. So I'm going to color code this for you guys, and I'm going to erase as we go through. So if I'm looking for f of 5, and I'm given an initial condition of f of 1, that means this has to be f of 1 plus the integral of 1 to 5 f prime of x dx. So I know I can plug in f of 1. F of 1 is equal to 5, plus I need to get the area between 1 and 5. So I get this awkward area here in blue. Well, we can use some of our easy shapes to figure out what this is. I know I have a semicircle, but if you notice, the semicircle is raised. So what I'm going to do is I'm actually going to find the area of this rectangle, because I know what the area of a rectangle is. And that area is the length times the width. So my length is equal to 1, 2, 3, 4. And I'm sorry, that's how wide it is. How tall I am, I'm 1, 2, 3. So I know that this green region is equal to 12, right? But I also know that in order to get the area of the blue, because that's what I'm really looking at, if I want to find this area right here, don't I have to subtract off this semicircle? So let's do the math for the semicircle. The area of a semicircle is pi r squared, and if you take a look, my radius is equal to 2. So 2 squared is 4. Since it's a semicircle, I have to divide that by 2, which means I need to take 12 minus this 2 pi. So I'm going to stick this down here to be 12 minus 2 pi. And that's going to give us 17 minus 2 pi. Okay? So I'm going to clear this out just so we can color the next section. So I'm going to clear all of this out right here. The next section says, and let me scroll down just a little bit, f of 11. So what we're going to do is we are going to do f of 1. Let me use a different color here. Let's use red. F of 1 plus the integral of 1 to 11 f of x dx, f prime of x dx. So we know f is equal to 5, and we need to go from 1 all the way to 11. So we've actually found this area right here, and earlier we said that was 12 minus 2 pi. And so if we continue that, I'm going to add 12 minus 2 pi here. Now I take the area of this, which is 1/2. My base is 2 and my height is 3. So that gives us 3. So plus 3. And over here, if I break this up, here's another triangle. So it's 1/2. My base is 1, 2, 3. The height is -2. So this gives me a -3. And the last spot is this little rectangle, which has a length of 1 and height of -2. So I do a -2 right here. And what we see is this 3 cancels that 3. I'm going to make more space right here. And I get 5 plus 12 is 17, minus 2 is 15. So our area is 15 minus 2 pi. Good. Alright, so let's go ahead and take a look at our next section. And once again, I'm going to clear all of this out just so we have more room. And what we notice is we're going from 0 to 1. So what we get is f of 1 is equal to the integral of our initial, so f of 1, let me redo that. It's f of 1 plus our initial condition of 1 to our endpoint of 0, f prime of x dx. So we have to use some of our properties, and we'll plug in that f of 1. But we notice I'm going from 1 to 0, but when we calculate, we usually go from lower to bottom. So I'm going to go minus the integral of 0 to 1, f prime of x dx. So I take a look at the integral from 0 to 1, and I notice I have a little triangle right here. I get 1/2, the base is 1, the height is 3, so that gives me 3/2. And so what we get is 5 minus 3/2. And if I want common denominators, 10 minus 3 is 7 over 2. Good. And finally, let's take a look at f of -4. And once again, I'm going to erase this right here. So if I set up f of -4, and let's just do this down lower so we have more room, we get f of -4 is equal to f of 1 plus the integral of 1 to -4 f prime of x dx. It's a 4 right there. And then what we notice is, once again, we need to flip this. So we do f of 1, or in this case, let's actually plug in our 5. Get 5 minus the integral of -4 to 1, f of x dx, f prime of x dx. Now the good thing is we actually have the area for 0 to 1, which was 3/2 from our previous example. And then I take the area of this triangle, so it's 1/2, the base is 1, 2, 3, 4, and the height is -2, so the 2's cancel and we get a -4. So what we end up getting is 5 minus the quantity of -4 plus 3/2. And if we do that math, we get 5 plus 4 minus 3/2, which gives us 9 minus 3/2. Oops, too much. We get 9 minus 3 halves. And then once again, with common denominators, 18 minus 3 is 15. And our answer is 15 over 2. Great. So what I'd like you guys to do is, in your blue sheet, let's go ahead and take a look at powder blue. And this would be page 4 and 5. And on your own, I'd like you guys to try, let's see. Actually, why don't we do all the even ones? So 2 to 6 even. Thank you.